In our last class, we introduced two new circuit analysis techniques, linearity and superposition. In superposition, the idea is to take a more complicated circuit and break it down into multiple simpler circuits by activating only one independent source at a time. In today's lecture, we will do two more examples with superposition before switching over to the main topic in this packet of notes, Thevenin's Theorem. In this example, we're asked to use superposition to find the voltage Vout, which is the voltage across these terminals here, as a function of V1, V2, and I1. So what we see here is we have three independent sources, a voltage source there, a voltage source there, and a current source there. In addition, we have a dependent source, a voltage-controlled voltage source here. What linearity tells us is that Vout can be written as a linear combination of the independent sources. So A1 times V1 plus A2 times V2 plus B1 times I1. Notice that the dependent source does not show up in that linear combination. Likewise with superposition, when we break this circuit down into three smaller circuits, we don't deactivate the dependent source. We only deactivate the independent sources. So let's do this here. So with superposition, the first thing we want to do is to activate V1 only. When we activate V1, what do we get? A resistor there, a resistor there, or V1, 4 kilo ohm, 1 kilo ohm. This current source is deactivated. Remember, a deactivated current source is an open circuit. Continuing, this voltage source here, V2, is also deactivated, so it is shorted. Remember, a deactivated voltage source is a short circuit. This dependent source is not deactivated because it is a dependent source. So its value is still 0.5 Vx with the plus on the right, the minus on the left, and Vx, the controlling variable, is a voltage across this 1 kilo ohm resistor. And we're asked to measure this voltage at these terminals here, and we're going to call this Vout sub 1 because it's only a partial voltage. It is the voltage due only to the source V1. When we go to analyze this, the first thing we see is that the voltage Vout is simply the sum of the voltage across this 1 kilo ohm resistor and the voltage across this dependent source. The voltage across the 1 kilo ohm resistor is Vx, the voltage across the dependent source is 0.5 Vx, so the first thing we see is that Vout is just 1.5 times Vx. So if we can find Vx, we can then find Vout. We can find Vx, however, through a voltage division. Notice that this 4 kilo ohm resistor and this 1 kilo ohm resistor are in series. Technically, they're not in series because there are these branches going up here and here, but because no current's going to be flowing through either of those branches, for all intents and purposes, the 4 kilo ohm resistor and the 1 kilo ohm resistor are in series. So that means we can find Vx from voltage division. So from voltage division, what is Vx? Vx is going to be the resistance 1000 over 1000 plus 4000, all of that times V1, or V1 over 5. So if Vx is V1 over 5, and Vout is 1.5 Vx, what that implies is that Vout sub 1 is just 0.3 times V1. We set that aside. So now we want to activate I1 only. So let's redraw the circuit here. Now the current source is present. We still have our 4 kilo ohm resistor and our 1 kilo ohm resistor. We still have our dependent source of value 0.5 times Vx, where Vx is the voltage across the 1 kilo ohm resistor. Now, the voltage source on the left is shorted. It's off, so it's a short circuit. Likewise, the voltage source on the bottom is turned off, so it's short-circuited as well. And what we're interested in is finding the voltage across these terminals on the right. We will call that voltage Vout sub 2. Once again, it's a partial solution to the output voltage. This circuit, like the one on the left, we can first see that Vout sub 2 is nothing more than the voltage across the 1 kilo ohm resistor plus the voltage across the dependent source. And so we see the V out sub 2 is once again 1.5 times Vx. So if we can find Vx, we can find V out sub 2. In this circuit, Vx can be found by a combination of Ohm's law and current division. If you look here, we know the current through this branch. It's I1. That current is going to branch into two different places. It can either go through the 4 kilo ohm resistor or it can go through the 1 kilo ohm resistor. It cannot go to the right through the dependent source because it's open circuited on the other end. So this is a classic current division situation. So the current through the 1 kilo ohm resistor is nothing more than I1 times the opposite resistance, 4 kilo ohms, over the sum of the two resistances. The voltage Vx then is that current multiplied by the resistance 1 kilo ohm. So what we see is that Vx from Ohm's law is going to be 1000 times the current through the 1 kilo ohm resistor. But the current through the 1 kilo ohm resistor is the opposite resistance, 4000, over 4000 plus 1000, all of that times I1. Basically, this is current division. Multiplying by 1000 is Ohm's law. So if you work out this math, we get that Vx is 800 times I1. We then combine that with the fact that V out sub 2 is 1.5 Vx. So we get that V out sub 2 is 1200 times I1. So we now found the contribution of I1 to the output voltage. We set that aside. Finally, we want to activate V2 only. So we redraw the circuit a third time. We still have our two resistors, 4 kilo ohm, 1 kilo ohm. The voltage across the 1 kilo ohm resistor is this controlling voltage Vx. We still have our dependent source, 0.5 Vx. Now, this third source is present, V2. V1 is off, so it is shorted. I1 is off, so it's an open circuit. Remember, once again, when we turn off independent current sources, they're open circuited. When we turn off independent voltage sources, they're short circuited. And we want to measure the voltage across these output terminals. Let's call this voltage V out sub 3. The voltage across that output terminal is nothing more than minus V2 plus Vx plus 0.5 Vx. So we see that V out sub 3 is equal to negative V2 plus 1.5 times Vx. So once again, if we can find Vx, we can now find an expression for V out sub 3. But what is Vx? If you look at this part on the left, once again it looks sort of like voltage division. Remember, there's no current flowing through this branch or through that branch. And so the 4 kilo ohm and 1 kilo ohm resistors are technically in series, even though they don't look like they are. But now there's no voltage source on the left here. So Vx using voltage division would be 1000 over 1000 plus 4000 times 0 volts or 0 volts. If Vx is 0 volts, then V out sub 3 is nothing more than negative V sub 2. So what we've done here is we've taken this one more complicated circuit and broken it down into three simpler circuits. 1, 2, and 3. We can then add up those voltages for each of the circuits to get the total voltage V out. So V out total is equal to 0.3 times V1, that is a contribution due to the V1 source, plus 1200 times I1, that's a contribution due to the current source, minus V2, what we just determined above, that is a contribution due to the second independent voltage source. And so now, using superposition, we were able to express the output voltage in terms of the three independent inputs, V1, I1, and V2, which is what we wanted to do. And the one thing you want to remember here is when you have dependent sources, you do not deactivate the dependent source. Notice it shows up here still, it shows up here, and it shows up here. You only deactivate the independent sources. We'll do one more superposition example. This is an example with an op-amp, and we're going to see the superposition is particularly useful with op-amps because it allows us to take more complicated op-amp circuits and often break them down into some of the simplest op-amp forms. This is the level shifting amplifier, so there's a voltage VA and then another DC offset VB. You could look back in your notes to see what the voltage Vout would be. We're going to rederive this input-output relationship using superposition now. We're going to do this by breaking this circuit into two simpler ones. First thing we're going to do is we're going to activate VA only. So with only VA activated, here's our source VA. You have a resistor R1 going into the inverting terminal of the op-amp. The non-inverting terminal of the op-amp is now going to be grounded. Feedback resistor R2, and the voltage at this output terminal we will call Vout sub 1. And notice by setting VB equal to 0, we're short-circuiting that point there. If you look at this sub-circuit, you see that it's nothing more than an inverting amplifier. You could analyze this by doing KCL at the inverting terminal of the op-amp, but you can also just utilize the result, and we know that Vout sub 1 is nothing more than negative R2 over R1 times VA of t. We set that aside. We can now activate VB only. So if we redraw the circuit now, we have the resistor R1 going into the inverting terminal. R2 is our feedback resistor. The non-inverting terminal is connected to our VB, which is grounded. And now VA is short-circuited, set equal to 0. And we're going to measure this voltage at the output. We're going to call it Vout sub 2. If you look at this circuit, it's nothing more than a non-inverting op-amp. Once again, we could analyze this by doing KCL at the inverting terminal, but you can also just memorize the equation, and we know that Vout sub 2 is nothing more than VB times 1 plus R2 over R1. We can now combine these together to get the total voltage Vout is just the sum of the output due to VA only plus the output due to VB only. And we get that Vout is equal to negative R2 over R1 times VA plus 1 plus R2 over R1 times VB. And that, of course, is the same equation that we derived earlier when we introduced the level shifting amplifier. So the question might arise, is it easier to break the circuit into two simpler circuits, the inverting amplifier and the non-inverting amplifier, or is it easier just to analyze the circuit as it is? It depends on how simple the simplified circuits are. It also depends on how complicated the original circuit is. But as I said before, even if this is not easier, I think it's useful to think about superposition because it allows you to really see the effect of each input acting alone on the output. So that concludes superposition. So we're now ready to start the main part of this packet, and that is Thevenin's theorem. Thevenin's theorem is one of those theorems that when you first hear it, it might not make a lot of sense. But once you start working with it, you find out that it's a very useful theorem, and it's actually not all that difficult to implement. So let's assume that we have a circuit, and I'll just put some different components here, a voltage source, some resistors here, maybe a current source there, some more resistors, etc. Suppose that you can find a place where you can divide this circuit into two parts connected just by two terminals. For example, maybe we want to divide this up right there. They connect at that terminal and that terminal. So let's consider a circuit that can be divided into two subcircuits connected at a pair of terminals. And let's call everything to the left of this red line subcircuit 1, and everything to the right of this line subcircuit 2. What Thevenin's theorem states is that if subcircuit 1 is linear, in other words, all of the components in it are linear components, and if there are dependent sources, both the source and its controlling voltage or current have to be in the same subcircuit, either both to the right of the dotted line or both to the left of the dotted line. Anyway, if both of those requirements are upheld, then what Thevenin's theorem states is that one of the subcircuits, let's call it subcircuit 1 in this case, can almost always be replaced mathematically by a simpler circuit called the Thevenin equivalent network, which consists of nothing more than a voltage source, we'll call it VOC, and a series resistance, we'll call it R Thevenin. In other words, what we're saying is as far as this right part of the circuit goes, the part that we're not simplifying, it doesn't know the difference between the actual circuit to the left and the simplified Thevenin equivalent. So once again, as far as subcircuit 2, which I'm going to call the load in this case, is concerned, the actual subcircuit 1 and its simplified Thevenin equivalent have identical effects. So why is Thevenin's theorem important? Well, first off, think back to this circuit here and imagine now changing this right part of the circuit, putting different resistors there. If you go back to the original circuit and try to analyze it each time, you're analyzing a more complicated circuit multiple times. If, however, you take the part of the circuit that's not changing and replace it by its Thevenin equivalent here, you still have multiple circuits to analyze, but they're multiple simpler circuits. So that is the first use of Thevenin's theorem. Another advantage is if you have part of the circuit that's unknown, you can take certain measurements, as we're going to see moving forward, that allow you to find the Thevenin equivalent model just from measurements. So that means that even if you did not have the circuit diagram for this part of the circuit, you could take measurements at those terminals to determine what this Thevenin equivalent model was. Third use of Thevenin's theorem is what we call maximum power transfer. We're going to see this towards the end of the packet, that as you change your load resistor, it changes the voltage across it, it changes the current through it, which means it changes the power absorbed. And you can use Thevenin's theorem to determine what the absolute maximum power that that load can absorb is. Another advantage is when analyzing loading effects of different measurement devices, for example, a voltmeter or an ammeter, or if you want to find the effects of a non-ideal source, for example, a battery, you can use the Thevenin equivalent model as well. Classic example of this. If you think about a function generator driving a circuit, what do we do when we model the function generator? We replace it by an ideal voltage source and an internal resistance of the function generator, RS. Does this mean that the function generator consists of only an ideal source and an internal resistance? Of course not. There's lots of electronics inside the function generator. But as far as this circuit on the right is concerned, it doesn't know the difference between the actual electronics that's inside the function generator and the simplified model, the Thevenin equivalent, which is VOC and the series resistance. So in essence, we've actually been using Thevenin's theorem throughout this course without really thinking about it. In lab, for example, when we've used the function generator, we model the function generator as a source, and we either took the internal resistance into account, we measured that, I believe, in one of the labs, or you just assume it's very, very small and you ignore it. But the bottom line is we use Thevenin's theorem all the time without even thinking about it. Another place where we use Thevenin's theorem, you've probably heard that you can model speakers as resistances. Many speakers are modeled, for example, as 8 ohm resistors. Does this mean that when you have a big speaker, all that it is a single 8 ohm resistor? Of course not. There's lots of electronics inside a speaker. But as far as the rest of the circuit is concerned, that speaker has the same properties as an 8 ohm resistor, so we model it as an 8 ohm resistor. That, once again, is Thevenin's theorem in action. So at this point, we're ready to ask the question, how do we find the Thevenin equivalent model? There are two things you need to find. The first thing is this voltage value, VOC. The second thing you need to find is this resistance, R Thevenin. So how do you find the two? Well, the Thevenin voltage VOC is simply found by measuring the voltage that appears across those terminals if nothing were connected to them. So you take this point where we're going to break the circuit up into two, we remove the right part of the circuit and measure that open circuit voltage. By the way, that's why this is called VOC. That OC stands for open circuit. So VOC is nothing more than the open circuit voltage across the terminals of the subcircuit you're modeling if nothing is attached. How do we find our Thevenin? The way you find our Thevenin, you take the subcircuit that you're trying to model and you deactivate all the sources and you measure the resistance looking into those terminals. And that resistance is going to be our Thevenin. And remembering when we talked about superposition, deactivating a voltage source means what? You short circuit it. And deactivating a current source means what? You open circuit it. Finding VOC is typically very simple. You can use whatever circuit analysis techniques to find that open circuit voltage. For finding our Thevenin, however, we're going to see that there are multiple approaches you can use. Some are simpler, some are more difficult, but depending upon the type of circuit, not all of the different methods work. So let's go over the different methods for finding our Thevenin, and then we'll do some examples along the way. So one of the easiest ways to find our Thevenin is what we call the equivalent resistance method. If the subcircuit that you're being modeled, what I'm calling subcircuit 1, contains only independent sources and resistors, so the key words, it contains only independent sources and resistors, you can often find our Thevenin analytically by just setting all the voltage and current sources equal to 0 and simplifying the resulting resistive network to get the equivalent Thevenin resistance. So we're going to do an example with this approach first. So here we have a circuit, and we're going to break it up right here. We're going to put the load on the right, we're going to call that subcircuit 2, and the circuit on the left, we're going to call subcircuit 1. And we're asked to determine the equivalent of the circuit as seen by the load using this equivalent resistance method. In other words, as far as the load is concerned, there's no difference between the actual circuit and this much simpler looking circuit here. Like that. And what we need to do is find out what our Thevenin is, and we need to find out what VOC is. Once we do that, we're going to use this Thevenin model to then find the power absorbed by an 8 ohm load if it is attached to this circuit. So the first thing we need to do is find VOC. As I said, finding VOC is you basically detach the circuit at these two terminals here and measure the voltage at that point. So we take our 20 volt source, 5 ohm resistor, 2 amp source, a 20 ohm resistor. So this is our subcircuit 1, and we leave these terminals open circuited, and by definition, the voltage across these terminals here is the VOC in the Thevenin model. So we can use whatever technique we want to find VOC. In this case, maybe a nodal analysis is the easiest. Let's ground this here. So the voltage at this node is what? That is VOC. So doing KCL, we can sum the currents leaving that node, that current plus that current plus that current plus that current is equal to 0. Let's see what we get. Current to the left is VOC minus 20 over 5. Current going down, current through the current source is 2 amps, but it's 2 amps going up, so the current going down is negative 2 amps. The current going through this 20 ohm resistor from Ohm's law is VOC over 20. Finally, the current going through these terminals, because that is open circuited, is 0. All of that equals 0. We solve for VOC. We get VOC times 1/5 plus 1/20 equals, on the other side, 20 over 5 plus 2. 20 over 5 is 4. 4 plus 2 is 6. We get VOC times 4 plus 1 over 20 equals 6. We solve for VOC. VOC is 20 times 6 over 5, or 24 volts. So we've done the first half of our model. We found VOC. Now we want to find R Thevenin. And the approach we're going to use is what we call the equivalent resistance method. Because the subcircuit on the left consists only of independent sources and resistors, we can use this equivalent resistance method. So what we do is we deactivate all the sources. So the voltage source we replace by a short circuit. The current source we replace by an open circuit. And the resistors we leave untouched. So we still have our 5 ohm resistor. We still have our 20 ohm resistor. Our voltage source was shorted. Our current source was left open. And we want to now measure the resistance looking into these terminals. These are these same two terminals here where we're dividing the circuit. We find the resistance looking into that. And it's fairly simple in this case. The 20 ohm and the 5 ohm resistor are in parallel. So R Thevenin is 20 ohms in parallel with 5 ohms. That is the product over the sum. 100 over 25, or 4 ohms. So at this point, we have now found the Thevenin equivalent circuit as seen by the load resistor. In other words, the resistor on the right doesn't know the difference between the actual circuit it's connected to and this Thevenin model here. We can now use this Thevenin model down here to solve the last half of the problem. Use this model to find the power absorbed by an 8 ohm load. So now let's set this RL equal to 8 ohms and find its power. Well, if that resistance is 8 ohms, what's this current? IL is going to be what? 24 volts divided by 4 ohms plus 8 ohms. That's 24 volts divided by 12 ohms. That's 2 amps. So the absorbed power for a resistor is what? I squared times R. 2 times 2 is 4. 4 times 8. 32 watts are absorbed. What really makes this useful, what if after doing this for 8 ohms we decide we want to find the power absorbed by a 10 ohm resistor or a 20 ohm resistor or a 100 ohm resistor? All you need to do is go back to the simplified circuit here and just replace RL by 10 ohms, 20 ohms, 100 ohms, whatever. The one thing I want to point out also is if you were to go back to the original circuit and put an 8 ohm resistor here and solve for the power, guess what? You're going to get the same 32 watts. I'm not saying that this circuit here and this circuit here are equivalent. What I'm saying is as far as the load resistor are, they're equivalent. This load resistor here does not know the difference between the yellow subcircuit above and the pink subcircuit down below. And that is what Thevenin's theorem is saying. Now we're going to look at another way to find the Thevenin equivalent resistance. And this is called the VOC-ISC method. It's a little more complicated than the equivalent resistance method, but we're going to see that there's some circuits where the other method doesn't work, but this method does. So once again, we have the same Thevenin situation where we're taking a big circuit connected to 2 nodes there and breaking it down into subcircuit 1 and subcircuit 2. And from Thevenin's theorem, what we're saying is as far as subcircuit 2 is concerned, there is no difference between the actual subcircuit 1 and its Thevenin model here. Let's look at the voltage-current relationship at these 2 terminals here. The voltage where the 2 subcircuits connect, VL, is equal to VOC minus the voltage drop across this R Thevenin. But what's the voltage drop across R Thevenin? The voltage drop across the resistance is the resistance times the current through it, which we're going to call this current IL. And so we see that VL is equal to VOC minus R Thevenin times IL. In other words, this equation here gives us a relationship between the voltage across the terminals where they connect and the current at the terminals where the 2 subcircuits connect. And notice it's a function of both VOC and R Thevenin. If we were to plot this on a VI plot, so we have IL, that's the current through the terminals, VL is the voltage across the terminals, what we get is a straight line of slope minus R Thevenin. And we're going to use this figure to find R Thevenin. So as I said, because the VI characteristics of a Thevenin equivalent circuit is a straight line, we can use any 2 points to describe it and to find the slope. But there are 2 points that make the most sense to use. Those would be the 2 points where this line intersects the y-axis and the x-axis. Where it intersects the y-axis is where the current coming through the terminals is 0, but that's nothing more than the open circuit voltage. So this point in the graph is nothing more than VOC, which you found earlier. How about this other point? This is where the voltage across the terminals would be 0. We call that the short circuit current, ISC. So the second method for finding the Thevenin equivalent resistance is you break the circuit down into its 2 subcircuits, and then you take the circuit you want to model and you take 2 measurements. One is the voltage across the terminals when they're left open circuited, that's VOC, which by the way you needed to find that anyway just to find part of the Thevenin model. But now what you do is you connect the terminals together with a short circuit and you measure that current going through that short. That by definition is the second parameter, ISC, the short circuit current. It turns out that R Thevenin is the ratio of VOC over ISC. So it's a very different way to find R Thevenin, but this approach is something you could do experimentally. You don't need a circuit diagram to do this. You could break the circuit down, leave the terminals open, measure the voltage, short the terminals together, measure the current, and the ratio of the open circuit voltage to the short circuit current gives you the Thevenin resistance. So let's revisit the same circuit we saw before, and let's use the VOC-ISC approach to find the Thevenin equivalent resistance of the circuit to the left. So we don't need to re-find VOC, we have that already. From the example a couple pages ago, we saw that VOC was 24 volts. But now, rather than shutting off the voltage source and shutting off the current source and measuring that resistance through the terminals, we're going to find the Thevenin resistance by finding ISC first. So to find ISC, you take the same circuit model, 20 volt source, 5 ohm resistor, 2 amp source, another 20 ohm resistor. But now, rather than leaving these terminals open and measuring the voltage, we're going to short them together and measure this current, which we're going to call I sub SC. So let's do this analysis. If I put ground here, notice because of the short circuit, the voltage there is 0 volts. We can now use KCL along here, and we see that that current plus that current plus that current plus that current has to be 0. So let's do the KCL. Current to the left is 0 minus 20 over 5 ohms. Current going down here is -2. The current going down here is 0 minus 0 over 20 ohms. In other words, there's not going to be any current going through that 20 ohm resistor. And the current going through this branch is what we're looking for, ISC. The sum of those 4 currents is equal to 0. You solve for ISC, you get ISC is equal to 20 over 5 plus 2, or 6 amps. From here, you can get R Thevenin. R Thevenin, by definition, is VOC over ISC. So 24 volts over 6 amps, 4 ohms. If you compare that to the example a couple pages ago, you see it's the same value, 4 ohms, but found via a very different method. So the Thevenin model, once again, is 24 volt source and a 4 ohm resistor. What this means is as far as the circuit to the right is concerned, all of this stuff on the left is equivalent to this model here. At this point, you may ask yourself, why would you ever use the VOC-ISC approach? The equivalent resistance method is much easier, and it is. However, the equivalent resistance method cannot always be used. The equivalent resistance method can only be used if the circuit you're simplifying contains only independent sources and resistors, which we saw here. So that means that if you have a circuit that contains dependent sources, you cannot use the equivalent resistance method, and you'd have to use something like the VOC-ISC method. So we'll look at another example showing that. So this circuit looks something like the circuit before, except now we have a dependent current source rather than an independent current source. Because of this, we cannot use the equivalent resistance method to find our Thevenin. So instead, we have to use the VOC-ISC approach. So the first step is to find VOC, which, by the way, you'd have to find even if you were using the equivalent resistance method. VOC you always have to find. So you look at the circuit here, and we measure the voltage at the terminals with nothing attached. And that voltage is VOC. So you have a 10 ohm resistor, 5 ohm resistor here. This dependent source is Ix over 2, where Ix is defined as a current flowing through that 5 ohm resistor going right to left. So let's use nodal analysis. Let's put ground here. So that means the voltage at this terminal here is the voltage we're looking for. Call it VOC. So the first thing we want to do is get rid of our control variable Ix. What is Ix? Ix is a current through the 5 ohm resistor. So it's going to be VOC minus 10 volts over 5 ohms. Then we do KCL at this top node here. That current plus that current plus that current plus that current is equal to 0. So doing KCL, the current to the left is VOC minus 10 over 5. Current going down here is negative Ix over 2. So it's minus Ix, which we have up above, is VOC minus 10 over 5. All of that over 2. This current is VOC over 10. And this current, of course, is 0. The sum of those currents has to be 0. We solve for VOC. We get VOC times 1/5 minus 1/10 plus 1/10 equals, on the right-hand side, we get the 10 over 5. 10 over 5, that's that. And then we also have this term. We get 10 over 5 over 2. Bring that to the other side. We get minus 10 over 10. So we get that VOC times 1/5 is equal to what? 2 minus 1, or 1 volt, or the open circuit voltage is 5 volts. We set that aside. Now, we cannot find our Thevenin directly. We cannot set the voltage source equal to 0 and the current source equal to 0 because the current source is a dependent source. Instead, we now need to find ISC. How do you find ISC? You take the same circuit, but now you short circuit the terminals together and find the current. We still have our voltage source. We still have our dependent current source. We still have the resistor here. Here are our terminals. Now we're going to short them together, and we're going to find this current ISC. 5 ohm, 10 ohm. That's still Ix over 2, where Ix is defined as that. This is actually an even simpler circuit. Because of the short circuit, the voltage all along here is going to be 0 volts. So let's analyze this. What is Ix now? Ix now is 0 volts minus 10 volts over 5 ohms, or minus 2 amps. We can now do KCL once again. On top here, that current plus that current plus that current plus that current is equal to 0. Current to the left, once again, is 0 minus 10 over 5. Current going down is minus Ix over 2. Remember, Ix itself was negative 2 amps. Current going through the 10 ohm resistor is 0, 0 minus 0 over 10. And the current going to the right is what we're solving for, ISC. Sum of that equals 0. Solving for ISC, we get ISC is 10 over 5. That's this brought to the other side. This is plus 1. When we bring that to the other side, it's minus 1. So ISC is 2 minus 1, or 1 amp. Our Thevenin then, using this VOC-ISC method, is VOC over ISC, 5 volts over 1 amp, or 5 ohms. So the Thevenin equivalent model for this circuit is a 5 volt source and a series 5 ohm resistor. What we're saying then is this complicated circuit here and the simplified circuit here are equivalent as far as that load resistor is concerned, RL. Whatever you put in on the right there, it doesn't know the difference between the big circuit on the top and the simplified circuit on the bottom, our Thevenin equivalent. So in this example, we found the Thevenin equivalent using our second approach, which is the VOC-ISC approach. And we had to use that approach in this example because we had the dependent source. So now let's look at a third method for finding the Thevenin equivalent resistance. Once again, this third method is more complicated than the second method, which was more complicated than the first method, but this third method, once again, is going to be more versatile than the other two methods. There are some circuits where this method works, where the second method and the first method don't work. And this is called the external stimulation method for finding the Thevenin equivalent resistance. Once again, you find VOC the way you normally do. You just open circuit the terminals and you measure the voltage, or you analyze the circuit to find VOC that way. But how do you find the resistance in this case? What you do now is if you're trying to find the Thevenin equivalent resistance of this subcircuit here, what you do is you deactivate all the independent voltage and current sources in the subcircuit. Remembering, if it's a voltage source, you set it equal to 0 volts, which is a short circuit. If it's a current source, you set it equal to 0 amps, which is an open circuit. And now you apply an external current source or an external voltage source. If you apply an external current source, you measure the voltage across it, called V external. If you apply an external voltage source, you measure the current coming through it, called I external. Either way, the Thevenin resistance is the ratio of V external over I external. So you either apply a current source and measure its voltage, or you apply a voltage source and measure its current. And this approach also gives you R Thevenin. But as I said before, and what we'll talk about later, is this method is more versatile. There are some circuits where this approach works, where neither of the two previous approaches work. So we'll finish off this lecture with one example showing this external stimulation method. This is the same circuit we just looked at before, and we're asked to find the Thevenin equivalent as seen by the load using this external stimulation method. So first off, VOC we don't need to refine. It's the same thing that it was before, 5 volts. So VOC is 5 volts, which we saw earlier. Now, to find our Thevenin, we do external stimulation. So let's redraw this circuit, deactivating all independent sources and adding an external either voltage source or current source. So we're going to turn off this independent voltage source, setting it equal to 0 volts, which is a short circuit. We still have our 5 ohm resistor. We do not turn off our dependent source. We only turn off the independent sources. So its value is still Ix over 2, where Ix is defined as the current through that 5 ohm resistor. We still have our 10 ohm resistor here, and then our terminals here. And now we apply either an external voltage source and measure the current coming out of it, or we apply a current source and measure the voltage across it. I'm going to apply a voltage source. I'm going to make life easy for myself and make it a 1 volt source. And I want to measure the current coming out of it. You need to be careful of which current you're measuring. You want to measure the current leaving the plus terminal. There's a plus terminal. You want to measure the current leaving it. Likewise, if you had a current source, V external is the voltage at the arrowhead with respect to the voltage at the other end. So the current we're measuring is the current in this direction. We'll call that I external. And we can use whatever method we want to find I external. What we'll see is it's actually fairly simple, because if you look at the circuit, we'll put a ground here, there are only two nodes. There's a node on the bottom here, goes all the way up to there, and the node on the top is here. Furthermore, because of that external source, we know the voltage at this blue node is 1 volt. So it's pretty easy now to find I external. We can do KCL by summing this current plus that current plus that current plus that current is equal to 0. Before we do that, let's find out what this I sub x is. Ix is going to be the voltage at the coming from point, 1 volt, minus the voltage at the going to point, 0 volts. Over here it's ground, divided by the resistance, 5 ohms. So it's 0.2 amps. We can now do KCL. The current to the left, I just said, it's 1 volt over 5 ohms, so it's 1/5. The current going down is Ix over 2, but Ix is 0.2 amps, so this is going to be minus 0.2 over 2. Current going down here from Ohm's law is 1 volt over 10 ohms. The current going to the right is negative I external. This is what we're solving for. Sum of all those currents is equal to 0. So what's I external? Bring it to the other side. It's 0.2 minus 0.1 plus 0.1, or 0.2 amps. Our Thevenin is what? The external voltage divided by the external current. The external voltage, we made it 1 volt, divided by 0.2 amps, 5 ohms, which is the same answer we saw using the VOC-ISC approach. And of course, VOC we got earlier, it was 5 volts, so our final model, 5 volt source, and a 5 ohm resistance. This concludes today's lecture. Next class, we'll look at a circuit where you have to use this external stimulation method. Once again, it's more work than the VOC-ISC method, which in turn is more work than the equivalent resistance method, but we're going to see that there are some circuits where you have to use this third approach. We'll look at that next class. Have a good day.